I don't think it is very useful to speculate on what God might or might not be able to do. Rather, we should examine what he actually does with the universe we live in. All our observations suggest that it operates according to well-defined laws. These laws may have been ordained by God, but it seems that he does not intervene in the universe to break the laws, at least, not once he had set the universe going.
In the cauldron of the early universe, no light could escape the dense, opaque fog of primordial gas. As this cosmic soup of atomic particles began to cool down, hydrogen atoms began to form, resulting in the universe's first bright, violent new stars, burning through the fog that once prevented all light from escaping the expanding universe. The James Webb Telescope will give us our first detailed glimpse of this early universe from which we and everything we know was born. The James Webb Telescope is a $10 billion endeavor. An endeavor that has eaten into NASA's limited budget, consuming 1/4 of NASA's entire astronomy budget for years. In the early hours of a tenuous launch date on December 24th, this $10 billion gamble was launched aboard the Ariane 5 rocket, a European heavy-lift launch vehicle from the European spaceport Kourou, French Guiana, carrying the next generation in human curiosity into space. French Guiana, a spaceport ideally located on the Earth's equator, was chosen to give the James Webb Telescope an extra push towards its final destination. The James Webb Telescope will not be in orbit around Earth like Hubble. It will be launched to a destination 1.5 million kilometers from Earth, Lagrange Point 2. Lagrange points are special points in space where small objects like satellites can stay in the same position relative to the gravitational bodies with which they are traveling. To operate correctly, the dark side of the telescope needs to operate at -233 degrees Celsius without a way to block out the heat from the Sun and the Earth. The telescope would be scorched at 83 degrees Celsius, nearly hot enough to boil water. This is a huge amount of heat to block, and to do this, the James Webb Telescope will carry a massive shield on its back like a tortoise. The sun shield needs to be light, strong, resistant to degradation from solar radiation, dimensionally stable across a range of temperatures, and reflective. That's a long shopping list of requirements, and Captain, a type of high-performance plastic polymer, manages to check all the boxes. Each layer of the Captain sun shield is incredibly thin. Layer 1, the layer closest to the Sun, is the thickest at 0.05 millimeters, while the next 4 layers are just 0.025 millimeters thick. Captain by itself is actually transparent, which isn't a fantastic property for a sun-blocking heat shield. Thankfully, the wonder material that is Captain can be easily coated with other materials. Each layer is coated in a 100 nanometer thick coating of aluminium, which gives the sun shield its reflective appearance. This reflective quality helps prevent heat transfer through radiation by simply reflecting the radiation into space, and with the gaps between each layer. The heat that is absorbed can't be easily transferred through conduction or convection. Heat could still transfer between each layer through radiation. Layer 1 itself is coated with a special silicon coating 50 nanometers thick, giving it its pink appearance. Silicon was used because it has high emissivity, meaning it emits a lot of energy that it absorbs as thermal radiation. Meaning the material will not hold onto its heat, which would give it time to conduct through the structure of the spacecraft to areas we want cool. This high emissivity silicon coating is applied to layer 1 and 2, the 2 hottest layers, helping them send their heat back out to space, away from the spacecraft, as fast as possible. These design choices are what allow the heat shield to maintain the massive heat differential between the hot and cold side. In order to fit inside the fairing of the Ariane 5 rocket, the sun shield has to be folded and stowed before launch, leading to some incredibly complicated mechanics to ensure it unfolds correctly when game time arrives. As the spacecraft is coasting towards L2, there are over 300 single points of failure in the unfolding sequence. 300 chances for a $10 billion, 25-year project to end prematurely. 107 pins holding the sun shield together have to be released on cue, to allow the system of pulleys, motors, cables, bearings, and springs to begin unfurling the sun shield into its precise, complete shape. This process will take 3 days, and once completed, the optical components will unfold and lock into place, completing the transformation process. But we are most certainly not in the clear. The likelihood of the tennis court-sized sunshield being struck by micrometeorites is fairly high, and because this is a thin layer of plastic stretched out under tension. A small tear caused by an impact could cause a runaway tear ripping through the entire sunshield. To prevent this, ripstop seams have been molded into the sunshield, which will arrest tears and keep them confined to a single portion of the shield without compromising structural integrity. The film has also been carefully molded with corrugations and other shapes to stiffen the shield as needed. This passive cooling system helps tremendously, ensuring the dark side of the telescope is shielded from the sun's heat, thus keeping its sensitive heat-detecting instruments at 40 Kelvin, which is about -233 degrees Celsius, but parts of the telescope, specifically the mid-infrared detection instrument located here, needs to be even colder to work correctly. It needs to be 7 Kelvin, just 7 degrees of the absolute minimum temperature of the universe of 0 Kelvin, and for this we need active cooling. The James Webb Telescope includes an innovative cryo-cooler for this purpose. The challenge in developing this cryo-cooler alone was immense and costing $150 million. Getting cold temperatures is just one small part of the design. Vibration has to be eliminated, as the tiniest movement of the telescope could cause massive blurs in the image as it attempts to focus on objects billions of light years away. That means eliminating moving parts where possible, and when that can't be done, incredibly precise machining and movement is needed to balance weights as they move. The golden mirrors are the most striking part of the telescope. Made of 18 hexagonal segments, 6.5 meters in diameter. The mirror surface itself is beryllium plated in gold, which is a unique and expensive material choice. There is the need for the structure of these mirrors to remain in an extremely precise shape for it to reflect light as desired. They can't bend and they can't warp with temperature changes, and they also need to be extremely lightweight to reduce launch costs. Beryllium is a lightweight metal, with an atomic weight of just 4. It's much lighter than silica glass, a more traditional mirror subsurface material. While being far more capable in dealing with the cryogenic temperatures, the mirror will operate at keeping its shape and not contracting so much that it ruins the carefully shaped curves of the mirror. While nowhere near as strong as steel, beryllium is much stiffer with a Young's modulus of 300 gigapascals. This means that while beryllium is easier to break than steel, it's harder to deform before it breaks, giving it excellent dimensional stability. On a pound-for-pound basis, beryllium is 6 times stiffer than steel, making it the perfect subsurface material for this mirror. However, it is not reflective, and for that, we need to turn to gold. Gold is not the best reflector of visible light, being particularly poor at reflecting the lower frequencies of the visible spectrum, but it is an excellent reflector of the infrared spectrum. Its unreactive nature ensures the mirror surface will not tarnish and lose its shine during operation. The mirrors of the James Webb Telescope are far larger than those of Hubble's, and to explain why, we ask Mike Mansell.
Well, I could tell you how much it's collecting. First, we're looking for stars or stellar objects or things that are approximately going to be a nanojansky. And to explain what a nanojansky is, a unit of brightness. It's very, very dim. We're looking for among the dimmest things there are in the sky. If I was to put a child's nightlight, puts out about 5 watts, put it on the surface of the moon and look at it from the Earth, that source would appear to be 20 nanojanskys. So we're looking for objects that are 1/20th as bright as that. To do that, you need a big telescope. Picture light as rain coming in. If you want to collect a lot of rain, you make a big, wide bucket. Well, even at the size of our bucket, 6 meters across, we're only collecting about 1 photon per second, 1 particle of light per second. And to put that in perspective, I'll go out tonight or any night and look at the brightest star there is in the sky. Your eye is probably collecting about 1 million photons per second from that star. So to see these very dim things, the dimmest things there are to see in the universe, you need a light bucket that's at least 6 meters in diameter.
To do that, you need a big telescope. Once fully deployed, the telescope will begin its calibration phase, with each mirror adjusting itself until each of the 18 segments has aligned correctly with the secondary mirror. A 0.74-meter convex mirror, which has 6 motors to adjust its position. These motors and control systems are so precise that the mirrors can adjust their positions in steps on the scale of wavelengths of light. creeping closer to alignment by increments of 1/10 of a thousandth the size of a human hair. That is an astoundingly accurate electromechanical system. The engineers of the James Webb Telescope performed this calibration test here on Earth. With a massive vacuum chamber that can be cooled down to the same temperature that the telescope will operate at, to ensure proper focus can be achieved once deployed. Again, Mike Mansell shed light on how engineers are planning on building the next generation of space telescopes.
It's my hope as an engineer, and after being 25 years on this job, that eventually our telescopes, the really, really, really big ones of the future, will be built in space. Testing James Webb, a telescope that's designed to work in space, has been a very difficult thing to do on the ground. And I'm hoping that someday we'll be building these things in space, testing them in space, tweaking them in space, and then deploying them in space that way.
We are on the frontier of a new space age, and the James Webb Telescope is a milestone on our journey towards being a more capable spacefaring society, venturing deeper into the cosmos than ever before.